Okay, let's jump right in. Hi everyone again. Today's meeting number 18 of the M2D2 series. And we are excited to have Noah Weber with us today to present how his and his team use machine learning for rational PIC design. Um, and a bit about the speaker before we start. Noah is served as a Chief Technology Officer at Cellular Therapeutics. He is a Kaggle Grandmaster and adjunct lecturer at Vienna University of Technology and Vienna University of Applied Science. Thank you so much, Noah, for accepting our invitation and looking forward to the presentation.
Thank you, Prudencio, definitely for inviting me, and I look forward to presenting and discussing to you guys this topic. Just to confirm, you see my screen, correct? Yes, awesome, nice.
Yes.
Then I propose I jump straight into it. So as Prudencio said, we want to see what is the process of utilizing machine learning for rational design of proximity-inducing compounds. What does these proximity-inducing compounds mean in the terms of targeted protein degradation? And I explicitly adjusted the title from prediction of stable ternary complexes to more general sense of utilizing the machine learning such that we can cover different facets of it, because it's in order to successfully design these compounds that are then actually going to pass the lab tests. There are multiple facets in the design process, and as we know, the biology, we're going to talk about it, is a lot more complex than just predicting whether the complex is stable or not. So we're going to go into all the details. But maybe first of all, why? What's the missing link in treating the disease, and what's kind of the needed motivation behind it? But we know that there's a lot of disease-causative proteins that are still undrugged, and with the standard inhibition, this has been proven to be particularly tricky. This includes, of course, the central nervous system diseases. I don't have to talk about time and cost. I think this is pretty much familiar. It's the inverse Moore's law, the Room's law, that states that the pharma companies are just becoming more and more inefficient, and they just cannot match with the needs, the therapeutic needs that we need to cover. So a lot of additional biotech players, especially AI biotech players, are coming in and trying to solve these problems from a research perspective. The standard, or one of the standard paradigms, is obviously inhibition. We try to traditionally inhibit the functions of the pathogenic proteins, but as we know, only 10 to 20%, and this might even be on the upper side, is actually inhibitable. So obviously we need some sort of alternative mechanism. Now, one solution to this story is degradation. Degradation is essentially, I would say, a technology that was developed a couple of decades ago, and a couple of companies have been spun out since then. But the story about it is that we can induce the mechanism, the natural mechanism of garbage collection in an organism. Like, as we know from a computer science, we can dispose these molecules in a targeted fashion and really choose which molecules we want to remove from our body. The next pillar, or the next important step in modeling this in silico, is ML-focused approach. So as the field of degraders, or PICs generally, is maturing, there's a lot more data that's being available there, and we could potentially make some interesting inference and address the needs in designing these degraders computationally. And finally, one of the core aspects, and that's exactly what's behind the prediction of the stable ternary complex, is one of the most important parts of the whole pipeline, is active learning. So how, and that's what I'm going to get into, is how active learning allows us essentially to make these predictions and explore the kind of the unknown space of the data of the molecules in a much more efficient way. I'm aware there has been previous presentations on this topic, obviously not in the degrader space, but something rather familiar that has been tackling different pharma aspects utilizing active learning. Again, I said it's a huge opportunity, and as we know, the Proteome showcases exactly this fact. So for different kinds of proteins, or thousands and thousands, there's just a huge need for potentially designing these sorts of drugs and different kinds of therapeutics could be developed here, and it's just waiting to be tapped into. And we know this, and this has been confirmed by the number of growing literature and companies in the last year. Just a very short overview of what are the advantages of degraders from a chemical point of view or from biological, because that will also come into the modeling or the computational part. When we look at across different features that are specific, we see that most of these technologies like RNA inference or biologics or inhibitors simply do not pose these all of the things that degraders pose. And it's very important to have these kinds of thoughts in mind once we go the modeling route. We have the hit candidate, and then we want to synthesize. The PICs, or the proximity-inducing compounds, encompass much more than just degraders. Degraders are maybe one of the most famous examples of the proximity-inducing compounds, but there's much more than that. A couple of examples I noted here, but the general gist of it is by inducing the proximity, certain therapeutic mechanism could be triggered, which could then have positive, or we would try to induce the positive effects in the body. I said this is a super growing field, and that just showcases the number of bivalent degraders in the clinic. So a lot of companies have been working on it since years and years now, using kind of non-computational approaches, or mostly non-computational approaches, in order to get these degraders to the clinic. And we know first clinical trials have been already initiated in 2019. A lot of these companies are also public, but it just showcases that the field is growing. And another great indicator is the number of publications. When you look at it, it's essentially exponentially growing in the last years. Now, coming to the biological part, so we need to understand exactly, once we want to even model it, we need to understand what does biology say about this topic, and how does this actually happen. And it's a pretty complex, Ubiquitin-Proteasome System is a pretty complex system, and this what I'm trying to depict here, and I'm going to walk us through very slowly, is maybe a narrowed down or distilled version of what is actually happening. But the gist of it is we have our target protein of interest. That's the blue molecule that you see here in the upper left corner, and then you have in between, you're trying to essentially connect it with the E3 ligase, which is again another enzyme, but it's connected with the whole E3 complex as it's depicted here. And on top of this complex, we have the ubiquitin, and ubiquitin is what we hope will come into the proximity of the lysines or solvent-exposed lysines on top of our protein of interest. And with that, it will connect and degrade or destroy our pathogenic protein of interest. Now, in order for all of this to happen, obviously there's a lot of interplays happening, but one of the essentially most important first steps is determining this stable ternary complex between the protein of interest and the E3 ligase, so not the complex, meaning making sure that the blue molecule together with the E3 binding moiety warhead linker and the red molecule, it forms together. So if we were to translate this very simply in simple words, this would essentially means we have two big molecules, three small ones, and we are trying to find a particular stable conformation for which this ternary complex will actually form, and then hopefully eventually degrade the pathogenic protein of interest. And as you can imagine, and that's exactly what we are going to go into there, it becomes a lot of computational decisions and what constitutes stability. How do we choose the linker molecule? How do we choose the warheads on the E3 binding moiety, right? So these all different decisions and choices are exactly what influences the, whether at the end of the day we have a valid molecule, the degrader molecule or not. And also subsequent ones, decisions that even aren't even included in this presentation, like selecting the E3 ligase that's suitable to degrade, right? So this is a huge research field and a question on its own. Currently, we only have a handful of ligases that are in use, and as we know, there's more than 600 ligases in our body that could be utilized for this case. So it's an important direction. And now coming to the computational part and entering the geometric deep learning, which was one of the enablers that allowed us to handle multiple components in predicting whether something is a viable hit or degrader or not. So one of the first ones is the geometric deep learning story. Again, I think for this audience, it would be really useless to go deep into this. We already had great talks organized that tackled these topics. One of them that I remember is can graphs learn chemistry, which they depicted kind of the positives and negatives, and it would be really useless for me to go deep into the why is this the powerful technology. But essentially it was a big enabler for us to tackle one important aspect that we wanted to model, and that was deep interaction prediction, meaning when we wanted to model the protein-protein interactions between that are involved in the ternary complex, meaning the complex between these three, or if you want to be detailed, 5 molecules. And in order to model that, we obviously needed not only something that's going to be accurate and adjusted and accurate for the specific use case of ternary complex prediction or the pathogenic proteins and ligases, but we also needed something that's going to be fast, because we needed to calculate these interactions almost on the fly, such that we can use the protein-protein interaction or the score that's involved in as one of the components or core components in the active learning loop for the ternary complex, which I'm going to obviously speak subsequently. And briefly, what has happened here, I just wanted to mention it because it was a big help in building the module that essentially predicts the stable ternary complex. This was another publication that we did. It's protein-protein interactions for ternary complexes. As I said, the core part is a geometric deep learning architecture that first takes from here the X-ray structure, I mean the 3D structure of the protein of interest, and first we need to then we need to find a suitable mesh surface and representation of the X-ray structure, and estimate the protein of this estimation of the protein surface that we are going to use. Then with different neural networks, I mean this is for the protein part, this is for the fragment. Then for both of them, for the fragment, we are going to map the 3D structures to a graph representation because it's such a small molecule. Then for both of them, we have a kind of initial quantitative representation of both of the molecules. Then we learn for both, and both are again encoded in graphs. We learn with intermediate neural networks. We learn chemical, geometrical, and local coordinate features, essentially finding embeddings that are informative enough to discriminate whether this constitutes a good interaction or not. And we learn this abstract embedding with deep graph representation learning. And at the end, we output whether on a surface patch level, whether this interaction is favorable or not, or whether it constitutes the desired interaction in our case or not. I think, yes, should we go with the questions now, or?
Yeah, I have one small question here. So, so you are talking about predicting the interaction on a patch level, but
Yes.
you also said you take into account the whole structure. So I'm not sure how this works. Could you kind of explain a bit more?
Sure. So you have to take, I mean, actually you're going to see it from a direct prediction here. So here's an exact prediction of protein-protein interaction between the BRD4 and cereblon. So BRD4 is the ligase and the protein of interest. And you see here that the binding site prediction, so these are the actual inferences here, the blue ones, and the binding site prediction for the BRD4 are essentially these point clouds or the surface patches of the inference. So you take the whole protein as a surface, but you, in order to learn and make the inference, you dissect it into the individual parts, meaning individual surface patches, for which you learn and make the inference on, right? So you can regard it as the prediction is essentially outputting you different patches that constitute interaction or not.
Okay, thank you.
We're just going to come to that, but just briefly, as I said, the publication is already available, and the most important thing was these architectures have been well researched and they were pretty interesting, but the most important thing for us from an application standpoint of view, okay, can we really make sure that we learn the interactions of the ternary complexes, meaning the proteins that are involved in the ternary complexes. And these are a couple of examples. So as you see here on the left side, for the protein A and B, you have the complex 6p and 8, and for the complex B, you have the 6HR2. And for these two, we have fairly high ORAC scores. The ORAC scores here are essentially a summary of what happens across all of the surface patches. So if we were to summarize or aggregate our inference power, not only for the patches that are supposed to interact, but also for the ones that are supposed to be non-interacting, this is going to be then aggregated into one singular number, and we would know, given the high ORAC values, is the model capable of discriminating what constitutes an interacting patch, a non-interacting patch in most of the cases, or not. And that's exactly what we showcased here. So we were at least for the ternary complexes that were known, and the crystal structure of the ternary complexes is known, and it's not really big. There's only 22 data points. For those that we know, we were pretty confident that we can essentially determine whether the interaction or whether the interaction on a particular surface patch is going to happen or not. And as I already went through this slide, this is exactly what we try to depict here. This is in the actual inference what happened, and as we see for the binding set, or exactly where the interaction was supposed to happen, we got the predictions, and also we got the high ORAC score, which tells us not only is the correct patches predicted, but also the incorrect were classified as they should. That was just one kind of introductory module that we needed, the protein-protein interaction or deep interaction module, where we will need the whole protein-protein interaction story in the formation of the stable ternary complexes. As we know, theoretically, this plays a big role, but how big of a role does it actually play, and how can we incorporate this information into the whole modeling story? Well, I think there's one of the two major classes in the degraders are the monofunctional and the heterobifunctional. The monofunctional, the best example are the molecular glues. I think they are also relatively famous, and the other side of the spectrum is the heterobifunctional, which are, for example, PROTACs. And the difference between them, with the PROTACs, we have this additional black molecule that you see here in the middle that's called the linker that connects the two molecules. And for the monofunctional ones, the PPI we know is very important, right? And the linked ligands, or the interactions between them, is not as substantial. Of course, it's important, but not as. And as we go more towards the heterobifunctional spectrum, it becomes the other way around. So PPI obviously plays a role, and it's important, but it's not the only story that we need to take into account, and the subsequent ones are then taking into account the interaction of the linked ligands in the molecules. And this plays a huge role, and we need to talk about then what role does it constitute when we are talking about the stable ternary complex. And if we were to try to model it, then we need to kind of have a approximated way of quantifying it from physics, or any sort of way that can tell us quantitatively what constitutes stability and what not, and how can we move towards making this inference. And well, obviously, I mean, we don't have to explain it. The delta G, Gibbs free energy, plays a very important role, and this is exactly what's supposed to happen, or what we hope it happens. So starting with substrates, we have a lower energy state when we look only at the binary complexes, that's here in the middle. And if we want to make sure that the stable ternary complex is formed, then the another cascade is going to happen, and we're going to find even lower delta G energies, and the cooperativity is going to be suitable. And what we don't want to happen, and what must be avoided, is that the delta G will be then increased after the state of the binary complexes, and this is exactly something that's tricky when trying to infer or model ternary complexes in respect to the binary complexes. We need to make sure that this cascade of water falling down the delta G waterfall is actually happening, and we don't get any spikes. So that's from a high level conceptual view of what we are trying to achieve here and what we are trying to minimize. Again, I think it's super clear in nature, everything moves towards a low stable energy level, and with ternary complexes, it's nothing different, and that's exactly what we want to achieve here. And now I'm coming slowly towards the active learning and how we are modeling exactly this aspect with machine learning. And in order to model it, again, there are multiple facets. So it's not only the standard inhibition story, you have the degrader, inhibitor, and then you try to see how this will be docked. So here are the multiple aspects. First, the degrader protein interaction, then the protein-protein interactions, and then what are the constraints that happen once I insert my linker, which surprisingly, even being the smallest molecule here, has big impacts on and outcomes on the whole ternary complex story. So we need to take these different interactions and constraints into account if we want to model the stability. And what we have done, and this is now going to be discussed, is that for most of these, for protein-protein interactions, we already explained it previously, we already built a deep learning or geometric deep learning architecture in order to learn these interactions. Same is true for different types of energy, for example, Wiener energy, etc. But this is exactly what's coming in the subsequent slides. Here I wanted to outline the different types of interactions and constraints that we needed to take into account. And I would claim that from a high level point of view, the whole story can be summarized in these 4 steps that we need to partake, and I'm going to explain all 4 of them. The first one is essentially, I would say, the simplest one, where we need to determine the protein 3D structure. Once we started, this was not available, but now with AlphaFold, I guess we are all familiar that this is now a reality, and it's not a problem to find a 3D crystal structure for the whole proteome. But the second part is then determining the protein ligand interactions, essentially docking the ligands to the protein, which is then going to be needed as the input for the subsequent steps. And again, the input for the third step comes from the second one, and that starts with the first deep linker generation, which is a generative model that I'm going to explain now, greatly variational autoencoder, to create artificially the needed linker for the given ligands in the question that we already docked previously. And once we have this whole structure, meaning the whole ternary structure, then we need to define or determine the best conformation or the best conformations under which the stable ternary complex actually forms. And that's exactly what we are going to do with the Bayesian optimization Bayesian optimization loop, meaning the active learning. And as I said, the first part in this third pillar is the deep linker generation, for which it was very important to determine the choice of the exit vector, as noted here. And this is an actual example of the 4V9H molecule. So determining the exit vectors is an important part as inputs. And this is what the deep linker generation module actually does. So we take the graph positions and active exit vectors of the fragments, and we use a variational autoencoder to generate this linker. Now, again, this is another publication that we did, and the details can be found there. I think there has been also previous presentations and work done on this part. I don't think it's particularly interesting to go deep into the architecture, but what I do think it's very important to outline here, at least from a practical standpoint of view, is that what we needed to incorporate together in the generative part is also multi-objective optimization. So what we wanted to avoid is only learning indirectly certain properties of the molecules and the linkers that we generated. We wanted to say beforehand, we want to limit ourselves for a particular area or a particular value of certain properties, for example, log P's, etc., and making sure that the linkers or the molecules that we generate for the linkers are the best examples that we need in this case. And even then, so after the generative part and the multi-objective optimization, we still get linkers that are good, acceptable, but not great in all different dimensions. And for that, we use automatic PIC filtration, meaning using different kind of in silico scripts, we just kick out values that are not suitable for us, toxicity, permeability, etc., because at the end of the day, as I said, choice of linker makes a huge difference. And we need to determine it before we even go into the stable Ternary complex modeling story. Okay, now I would claim the core part or the most interesting part is the Bayesian optimization or active learning for Ternary complex prediction. This is again a publication that we are almost done. We just need to apply refinement for it, which is essentially MD simulations, and this is going to be available, but everything else is done, and all of the steps that I outlined here are executed, and we have already validated the outputs in the lab, which I'm going to come to later on, and we are going to see what does it actually do, I mean, concretely in the lab. But the whole procedure could be summarized in four distinct steps. How do we determine the stable Ternary complex? First, we need the inputs. We need to initialize the inputs, and I already alluded to this previously. So the picture A, we need to have the linker, or we need to find the suitable linkers for the warheads that we already pre-selected, and then we need to dock the warheads or the E3 binding moiety to the respective ligase and the protein. This is exactly what happens here. And once we have all of these molecules docked, so they are now one molecule, we can proceed to the next step, which constitutes the Bayesian optimization. And this is kind of the core of how and where the Bayesian optimization is being applied to. This might look maybe a little bit complex, but we are going to go step by step, and you will see that it's pretty straightforward. So starting from the upper box of all possible conformations. So we have kind of Ternary complex, but they are all in different conformations, and we don't know what constitutes a good one or not. So it's this huge space of possible options combinatorically, and we need to find a way to parse the space in a lighthouse kind of manner, such that we explore the points that are interesting or that we aren't sure of, but we exploit the points that are already interesting or that we already evaluated, and then we slowly move towards the space where the stable Ternary complex happens and where the kind of the desired part of our space is located at. And the where we start from is we start from the couple of data points that we need to initially evaluate. So we are starting here with a couple of points, and with Bayesian optimization, essentially what we are trying to learn is this black box function for which we don't know the true values, but we are trying to approximate them with certain objective function. This objective function that constitutes or depicts, so to say, the goodness of our sample data points is exactly PPI fitness, constraint fitness, and the PROTAC fitness. So there are a couple of fitness functions that essentially are there to quantify how good or how good do we believe that this conformation is. I mean, the final combined or objective functions is essentially saying to us, this is something that's valuable, or this is something that's not valuable, and it takes different interactions into account. So as I said, initially the PPI fitness interaction is super important, but this is not the whole story. Second aspect is, how do we make sure that the PROTAC is inserted into in between the two proteins in a stable way? So we need kind of the constrained PROTAC fitness such that the energy is still minimal, even once or after the PROTAC is fitted inside of these two, or between these two molecules. And once we have this objective function, meaning these are the Y or the labels, as you may, and we have our data points, meaning our conformations. We use these X and Y points to train our surrogate model, which is a Gaussian process, such that we can essentially quantify how certain or uncertain are we in a particular future conformation, right? We want to explore the unknown space and exploit potentially what we already know. And in order to make these decisions on what do we actually explore or exploit, we have an acquisition strategy, which is super straightforward. It's UCB, upper confidence bound, which is, I think, pretty omnipresent and used in these scenarios, but we obviously evaluated it for our use cases, and we saw that this is exactly what allows us very sample efficiently to determine after approximately 2,000 to 3,000 iterations what constitutes a stable ternary complex and what not. And this is exactly how this loops goes. So we start with a couple, we determine the objective function, we train the surrogate model, then we explore a couple other parts of the space. We decide whether we want to explore and exploit. I mean, it's essentially a hyperparameter that we must decide, and then we repeat the process. Hopefully, in the same process, we are converging towards the most optimal space. And after a predefined number of steps, which we back tested, we have our final valid complexes, meaning the complexes that we predict are suitable to be ranked as stable. But that's not enough. What we then need in step 3, even after using Bayesian optimization, is we need to perform local optimization with simulated annealing of the PROTAC stability score. So PROTAC stability score is our proprietary score where we wanted to take into account different energies that need to be fulfilled such that the suggested molecules are even better than what we previously have outputted from the step 2. And the core part of it, or let's say the proprietary part of the whole step 3, is the definition of the PROTAC stability score, which constitutes from Wiener energy, which is the E with a V at the top with the exponent V, and the restoring energy, which is E Y with the R exponent. And these two energies measure, first of all, the combination of the intermolecular and internal energy of the conformer, and the restoring energy is the deviation of the E3 binder and Warham from their constrained positions in the particular RRT. So what this essentially is saying in a very, very high level overview is how confident or how stable can you fit the PROTAC in the whole ternary complex situation. And the new parameters are hyperparameters that need to be learned and need to be adjusted for in a particular setting. And what we have observed kind of from research or trial and error is that exactly once we use this step 3, we can discriminate very efficiently from whatever mistakes the previous Bayesian optimization step made, and we can filter out the complexes that were bad and pass through the complexes that were good, which then get finalized in the step 4, which constitutes of actually 3 components. clustering, air energy filtering, and cluster re-ranking. Clustering is essentially exactly that. We take different sets of RRTs, which is, again, I have to just reiterate, I might have not mentioned that the RRTs is the relative rotations and translations. So it's this 7-dimensional space of conformations, right? So you fixate protein of interest, and then you rotate the other part, relative rotations and translations, and you find these different different conformations or poses, and you try to navigate exactly the space, 7-dimensional space of the RRTs. And as I said, we want to cluster in the step 4 exactly in the space of RRTs, where we use, hopefully, depict a very different or diverse set of clusters with combination of the RRTs and the PPI score and the PROTAC stability score, such that whatever the final set of the structures that we predict, they are not in a same subset of the space, but they are pretty different from each other. Then after clustering happens and we have these different clusters of potential candidates, we use air energy filtering, which is essentially taken from HADOC. It's pretty, I would say, familiar and standard docking protocol that we used here, and we evaluated it, and we saw exactly in this diagram here, you can see a correlation for different complexes, 6X, 6PN7, and 6H1. You can see that the air energy is correlating pretty well with the y-axis, which is the DockQ score. DockQ score is based on the Capri metrics. It's essentially a way of quantifying the native or non-native scores. And for certain thresholds, we remove the complexes that have bad air energy score, and meaning very low or very negative, and the ones that are close to 0 we will retain. And finally, what happens is the cluster re-ranking. Once we have finished with the air energy, we re-rank the remaining clusters using the PROTAC stability score. PROTAC stability score, again, we mentioned here. And why we did it, what's the reason behind it? It was essentially a kind of a quantitative research where we had these different data points, and we just saw what does produce at the end the best hits or the best selection of the candidates. And that's step number 3. You can regard it as a very high-level global docking approach, where in this space of relative rotations and translations, 7-dimensional space, you can name it coarse-grained, we do this optimizations to find stability. And of course, what's still missing or what's still essential is the classical MD simulations or the refinement approach, where we need to make sure that on the sort of atom level that everything is aligned and that the energy is actually minimized also there, since we don't include in our Bayesian optimization, we don't include these higher dimensional space or features. Reason for that is pretty simple. As we know, Bayesian optimization, but I think generally any optimization suffers from high dimensionality. So what we observed is that once we explode the dimensions, it becomes very, very expensive procedure. As I said, the final step is the refinement step. We want to perform MD simulations and make sure that we take the compounds that are already very close to native or non-native, that we take them from there, and with these MD simulations with implicit solvent, we improve them subsequently a little bit such that they achieve the status that they need to achieve. And in order to do that, there are a couple of pre-processing steps that we need to do. It's kind of classical standard MD simulations, but at the end of the day, we get the rank of PICs by comparing their relative energies, and we have a virtual hit. And what happens with this virtual hit, and this is, I have 2 slides just to showcase the validation, and I'm done. So for example, this slide shows when we measure it with a Capri score, which is kind of standard here, it shows that for most of them, we achieve high almost near native values without the refinement. So everything you see here is without the refinement, and with refinement, this is going to then be improved subsequently. And what this allows us, as I said, and that's the whole selling point of the Bayesian optimization, is we can achieve these screenings very, very cost efficiently with the Bayesian optimization, because we don't have to execute full-blown MD simulations with thousands or hundreds of GPUs, and we can have outputs for the refinement in less than an hour. So everything that you see here before step 4 takes, with the preparation and everything, takes maximally a couple of hours. And the whole execution of Bayesian optimization is under an hour. And you get whatever you need for a couple of picoseconds refinement with MD in very, very blazingly fast. And the results, as I said, almost near native structures. And when we go to the lab and say, you know, this is all great and perfect, but these are numbers, no chemist that's worth his money will believe any computational methods. We will always look for the validation in the lab. And that's what we got with our initial tests. So with the Western blot validation, we got 2 hits that had Dmax values over 50, and 5 of them had Dmax over 25%, which essentially showcases that for these 2 degraders, the CTX410 and CTX411, the degradation of the protein will happen. For this initial validation, and that's my final sentence, is there is a very big improvement over typical virtual screening hit rates, which are to 1%, and we still have to do further validations in lab in order to confirm and generalize these numbers. But it's looking pretty, looking pretty interesting thus far. And that's it. I would be very happy to answer any of your questions.
Great. Thank you so much for the presentation. It was a great one. Learned so much. Floor is open for question. If you have any question, please raise your hand and open your mic. Okay. If there is, before people jump in, I can I can go first. So I have one question in the chat. So basically, on the first step of the, if you can go back to the slide, please.
Sure.
No, sorry. Yeah, this one. Thank you.
Yes.
Yeah. So on the first step, what type of resolution you need to, like, so you go from the sequence to the structure, what type of resolution you need? And because we were talking about AlphaFold, then one of the main concern of AlphaFold is actually the resolution that they output, right? And I was wondering if you need kind of high resolution structure to be able to work through the whole pipeline.
Yes, this is exactly correct. It's usually what we do is that, depending on the analysis, but we cut them off if the resolution is not under 6 to 7 angstroms.
Okay.
I mean, usually, of course, we're going to be very confident. The lower the resolution, the better it is. But it's a big problem. So if this is bad, then you are essentially inputting bad data that are then going to just skew whatever you learned in the process.
Okay, I see. One follow-up question is not follow-up, but another question. I think I very much understand step 3, but I'm not sure I understand the link between step 2 and step 3, because in step 2 is more or less the docking on the 2 separate proteins. And in step 3 is just finding how the conformation between the different proteins, right? And I'm missing the link. Like, if normally step 3 should not happen before step 2, like, I'm not sure I understand that part. So do you mind going on?
Okay, I'm going to repeat it very, very briefly. So in order to determine the conformations, you need to have some sort of first or initial ternary structure, right? And in order to have this initial ternary structure, you need to if we think back to the 5 molecules involved in the story, right? The very brief, very high level, you have the proteins, the warheads, and the linker. You need to connect them initially together in a sort of reasonable sense, and that would be the step 2, the protein ligand interaction or the docking, such that you can at least start generating these different conformations with different poses. And if we weren't to do that, right, how would we even know where to position correctly our ligands? And how would we even connect the ligands with the linker if this happens after the Bayesian optimization loop? So, long story short, in order to find the conformations, they already need to be connected together.
Okay, I think now I understand what was missing in my logic. So basically at step 2, you find what bind to every one of the protein, and in step 3, it's just adding the linker and adjusting the conformation. So like in what I understood, it was like in step 2, you already have the kind of the whole binder of both protein. Yeah, that's good. Thank you. There's a question from Bruna Souza in the chat. So, Bruna, do you mind opening your? Okay, so the linker molecule is built based on the PPI or the predicted pocket by docking?
Yes, so there are different actually caveats here that we already know from literature. So for one example, I think that's kind of what the question was alluding to. What we know from literature is that interaction between the protein of interest and the linker is also an essential one, which you can use in order to discriminate whether it's a valid linker or not. So depending on this, you can think of it as protein ligand interaction between the protein and the linker. If this is not suitable, then this is again a potential filtration step for which you want to kick out these filters, but not the only one. It's one of the components that take into the account whether this is suitable or not. The other one is then obviously the linkers ligands or the linker warhead discussion and how they are interacting and fitting in the whole story. So the short answer is taking all of these interactions into account.